All right, so in chapter 17, we're just laying the foundation for what you're going to be doing in chapter 18. So in our last lecture, we talked about Ohm's law, which is this equation up here. It says that voltage, delta V, is equal to current times resistance. The way I like to teach this equation is by rearranging it for current. So current is voltage over resistance, just doing the algebra. Now let's start with current. A few things about current before we look at what Ohm's law says. So yeah, according to Ohm's law, current is voltage over resistance. But there is a basic definition for what current is. So the symbol for current is capital I. The basic definition for current is charge per time. So Q is charge, T is time. We measure charge in coulombs. We measure time in second. So this gives us a unit of coulombs per second, which has a name, and that's called the amp. Okay? Current is measured in amps, which is coulomb per second. Now, as with everything else in physics, the direction of current is going to be defined as positive charge motion. So to figure out the direction of the current, you have to look at the battery. So here I have a diagram. In the last lecture, we talked about how to diagram circuits. This right here, that's how you diagram a battery. You're not going to do a cute little picture, of like, your little battery with a bump on it. Pause. Don't do that. The way you do a physics battery on a physics diagram, you simply do long line, short line. The long line is the positive terminal. The short line is the negative terminal. So if you imagine you could climb inside this wire and look at a little positive charge, which way would that little positive charge want to go? Towards the positive terminal or away from the positive terminal? Away. So you figure out the direction of current. So in this diagram here, the current is going to be going around the circuit like this, clockwise. Okay? Like that. And then back into the battery, like that. Now, the weird thing here is what really moves through an electrical circuit? Electrons. In fact, positive charges don't move. That's you find the positive charge in the nucleus. That's not going to be moving. In reality, it's electrons that move, but it doesn't matter. We're still going to define current flow as positive charge motion, even though in reality, positive charges don't move in a circuit. Okay? So we've got the definition for current here, and we've got the direction of current covered. You always look at the battery when you're figuring out direction of current. Now, looking at Ohm's law, so I've rearranged Ohm's law here for current. Current is voltage over resistance. Voltage is found at the battery. Okay, whenever you're given a battery, there's going to be some voltage. Think about voltage as the driving force of current. If you don't have voltage, you're not going to have current. Okay, now how does voltage affect current? If you look at this equation, if voltage gets bigger, what's going to happen to current? It's going to get bigger. What's the other thing that affects current? Resistance. Now, why do we call it resistance? I mean, there's a reason we call it resistance, because it's putting the brakes on current. As resistance goes up, current goes down, which makes sense. It's just like the charges if the resistance gets bigger, the charges have a harder time getting through the circuit, which therefore lowers the current in the circuit. Okay, resistance. Let's talk about this. So the unit for resistance is this guy here, and you call this guy an ohm, O-H-M, and an ohm is equivalent to a volt per amp. Okay, ohm is volt per amp. So what is 6? Here we have 6 ohms. That means 6 volts per amp. What the heck is volts per amp? Well, what this is telling you, this resistor, to have 1 amp flowing through it, how many volts do we need across it? 6 volts. This resistor will have 1 amp in it if there's a voltage of 6 applied to the resistor. Does that make sense? Volts per amp. Okay, this guy right here, this symbol represents grounding. If you see a circuit diagram, not all circuit diagrams indicate a point where the circuit is being grounded. But if you see this symbol right here, what that's telling you is that at that point where the grounding connects to the circuit, they're telling you that the electric potential at that point is 0. It's kind of like your 0 point for volts. Because remember, when you deal with volts, the thing that's going to matter is going to be the change from one point to another. So look, this point right here is 0. So how many volts would that be, the negative plate? Still 0. So 12-volt battery, so what does the positive plate have to be? 12, right? Because this is a delta V. The battery here, its delta V is 12. So if the negative plate is 0, which I know it is, how do I know that the negative plate is 0? Because you come straight down from the negative plate, what do you see right there? The grounding, and that's telling you the point where you have 0 volts. So as you cross this battery here, we go from 0 volts to 12 volts. So how many volts do we have at this point right there? 12. How many volts right here? 12. How many volts right there? 12. How many volts right here? 0. So here's the thing I want you guys to notice. As you go around this circuit, and this is the simplest of all possible circuits. It's the simplest circuit. 1 battery, 1 resistor. It doesn't get easier than that. Next chapter, we're going to look at problems where you have 2 resistors, 3 resistors, 10 resistors. But no matter what the circuit looks like, whenever you make a complete loop in a circuit, so let's do a complete loop starting right here. So notice that when I cross the battery, when the current crosses the battery, we are moving from 0 to 12 volts. Is that a voltage gain or a voltage loss? It's a gain. Now, if you think back to chapter 16, the definition for a volt is it's basically energy per charge. That was what a volt was, potential energy per charge. So when you cross the battery, you could say voltage gain, but that's just a fancy way of saying what? Energy gain. Okay, now come over here to the resistor. Notice that we're going from 12 volt to 0 volts. As we cross the resistor, we have a voltage loss, which is just a fancy way of saying energy loss. And if you think about this, it has to be true. You know, as the charges come into the battery, they're picking up energy, and then they go out to the resistor. And this resistor here could be a light bulb, it could be a hair dryer, it could be your iPhone. What happens in a resistor? Energy gets used. So it's like you got this cycle of energy gain, energy loss, energy gain, energy loss. The physics way to say that is voltage gain, voltage loss, right? You gain voltage in the battery, you lose voltage in the resistor, and they have to be equal. The charges cannot keep a little bit of energy like for a rainy day. You know, it's like if you think about money, I always relate things to money. Every month the school district pays me an exorbitant amount of money. It's ridiculous what they pay me. So this is just like I'm rich. But anyway, but they don't have a policy. The school district does not say, Spalding, the money you gain must equal the money you spend. They allow me to keep some, right, for later use, right? It doesn't work that way for charges. The rule is when charges come through the battery, they're going to be given energy. When those charges go through the resistor, they must release all of the energy. They can't keep any for later use, right? Because otherwise the charges could store up energy, store up energy, store up energy, and then one day take us over, okay, with all their energy that they stored, okay? All right, where to from here? So let's just clean this up, revert this back. So look, here's how you would use Ohm's law. What is this? I don't know why I did that. Weird. Okay. Okay, how would you go about finding the current in this circuit? So look, the current's going through like this. Okay, so you go to this guy right here, take Ohm's law, rearrange Ohm's law. I is delta V over R. This resistor right here is 6 ohms. Okay, so the resistance is 6. An ohm is a volt per amp. Now, how many volts are across that resistor? Well, look, 12-volt battery, that means 12 and 0. So how many volts right there? 12. How many volts right here? 0. So how many volts are across that resistor? 12. So the volts cancel, and you get current is equal to 2 amps. That make sense? Okay, so that's really the basics of circuitry. It'll get harder next chapter, but one thing that we have to talk about is power. So where is my... Oh, here we go. Okay, so power. You are going to come across problems where they ask you to find the power output of a resistor. So, first thing, recall the basic definition of power. You learned this first semester. It was in chapter 5. The basic definition for power, you could look at power as being two things. You could say that power is energy per time, and that's totally acceptable. Or you could say that power is work per time. Now, both of these two equations are equivalent because what do we measure energy in? Joules. Time is second. A joule per second is called a what? That's a watt. Okay, work is measured in joules. Time, second, that's called a watt. So sometimes you're going to look at power as being energy per time. In other cases, you're going to look at it as work per time. Okay, see my little circuit board I have set up over there? I got light bulbs on. Are those light bulbs doing work? No. But are they using energy? Yeah. So if you're talking about a light bulb, you're going to be thinking about power like this. All right? You'll have problems where you have a little electric motor, and the electric motor is like lifting up a mass or something. Now, in that case, could you talk about the work done by the electric motor? Yeah, so then you'd be looking at power like this. So it depends upon the circumstance. It's either going to be energy per time or work per time. Now, check this out. So we've defined what power is. Again, power is work per time or energy per time, which gives us the watt, which is a joule per second. Now, in a circuitry problem, you could have a situation like we just had where you got a battery and you got a resistor like this. So I don't know, let's say that's a 20-volt battery. If that's a 20-volt battery, what are we saying? If it's 20 volts, we're basically saying the negative plate is 0, positive plate is 20. So how many volts do we have right there? 20. How many volts do we have right here? 0. So then the voltage across the resistor is the same as the voltage of the battery because there's only one resistor. But now look, you got a current, you got some current going through here. Check it out. Circuitry power equations. There are 3 of them. There are 3 power equations that apply to circuits, and you have to have all 3 of them memorized for the quiz and the midterm. I'll give you the equations, but you got to have them memorized for the quiz and for the AP test. So look, memorize this first one. If you have this equation memorized, the first power equation for circuitry, you can easily figure out the other 2, which I'll show you how to do. But look at this. What is current measured in? What do we measure current in? Amps, which is what? Amp is coulomb per second. That's what current is. All right. Volts, voltage. What is volt? Joule per coulomb. What cancels out when you multiply these together? The coulombs cancel, and you get what? Watt. You get what? Watt. You get what? Watt. You get what? Watt. You get a watt. You get what? Watt. Look at joule per second. Watt. Okay? You guys with me on this? You multiply current times voltage. It comes out as joules per second, which is watts. Now, how do you get the other two power equations? Because you want to memorize as little as possible. At least if you're into memorizing, you might want to just memorize. But look, take my advice here. Memorize this one. Now, how do you get the other two? You take Ohm's law. Take Ohm's law, plug it in right there. What's that going to give you? I squared R. Right? Then what you do is you rearrange Ohm's law. I is delta V over R. Plug that in for I, and then you get the third equation, which is delta V squared over R. So these are your three power equations for circuitry. The way these problems typically go is you're going to go like this. You're going to start by using one of these, right? You'll figure out the power of whatever it is, and then once you figured out the power, then you can answer the question by using one of these, right? It's like you figure out what P is from over here. Like, okay, now I got my P, so now I can solve for whatever they're at. Like, let's say they're asking you to solve for time. Then you solve for T. You know what I'm saying? So typically the way the problems go, you're going to be using these two equations, these two ideas together. You solve for what power is, then plug it into the basic definition of power. Okay? Oh, and then the final thing, since this is a review of Chapter 17, Chapter 17 asks you about the resistance of a wire. Oh, did I just save that? So say this is a wire, right? Do wires have resistance? They do. So just a quick word on this. If you're given a circuit like this, look at, if you're given a circuit like that, the thing that we assume about the wire, like this part right here, we assume that this part has how much resistance? 0. And that all the resistance is in the resistor. That's what we assume. However, they are going to ask you questions about the resistance of a wire. Because why it's true that wiring does have resistance built into it. So the equation for finding the resistance of a piece of wire is this equation here. Resistance equals, now this cursive P there, that cursive P there is called resistivity. And all material has their own resistivity. You got to look it up in the book. Copper has it, has its own. Steel, aluminum, wood, plastic, rubber, you name it. If it's a material, it has a resistivity. Okay? So you got to look that up. It's unique to each material. Now, what is L? L is the length of the wire. The longer it is, the more resistance there will be. A, it's not amps, it's area. It's the cross-sectional area of the wire. So what's going to have more resistance? What would have more resistance? Let me draw you two wires here. So I drew a fat one and a skinny one. Which of these two wires will have more resistance? The skinnier one. The fatter one has less resistance, right? Because if A gets bigger, then R goes down. Right? So that's how you calculate resistance.